Hello everyone and welcome to the front of my house. It's a beautiful, beautiful day today, so we figured we can do this one outside. So today we're talking about insulators and conductors, and these are opposites, and they're both things that are terms talking about how well a material allows energy through. And for our purposes, we're talking about electrical energy. So let's just give an example of a conductor. So a conductor is something that allows things through very, very easily. An insulator is the opposite. An insulator is something that does not allow things through easily. So you may have noticed, if you've been on a train recently, there's a person there, he's called a conductor. He helps people along onto the train, tells them where we're going, what the next stop is, collects fares, all that, and that's because his job is to move people from one place to another. Practically for you, in terms of electricity, you've been using conductors, you probably use them every single day anyway, but we've been using them in this class when we've been using the wires. The wires are made out of metal. Metal is a very good conductor. You plug it into the battery, you plug it into the light, it allows electricity through it. This wire right here, can you see this? This is another conductor. It's conducting the electrical signal generated by my microphone to my camera, and that's how you can hear me. We use conductors when you plug something into the wall. Metal is an excellent conductor. That's why they use it for wires. So let's talk about insulators, and insulators are the opposite. Insulators do not let things through. You have insulation on your house. Insulation stops the flow of heat in the case of insulation for a house, and what that does is it lowers your heating bill in the winter and it lowers your AC bill in the summer, because when you turn your AC on, you're not cooling the entire neighborhood, you're just cooling your house because it's sealed in. Similarly, if you have your coat on, your body generates heat, and ideally it wants to keep most of that heat in. It wants to get rid of some of it, that's why you sweat and all those fun things, but it also wants to keep it in specifically when you're cold. It's in the winter when the world is cold, and so you might wear a coat, and when you wear a coat, that traps heat in. Right, that's an example of a good insulator. So purely in scientific definition terms, a conductor is something with a very little resistance, meaning it doesn't stop the flow of energy. An insulator is something that does stop the flow of energy, meaning that it has a very high resistance. Now, neither an insulator nor a conductor are absolute, meaning that even though a conductor is very easily passing on power, in this case electricity, it's slowing it down a little bit. For instance, in the case of your house, you have insulation on your house. It's not absolute insulation. It doesn't completely seal in all the heat inside your house, which is good because it would probably catch fire. And in the case of a conductor, most conductors do provide some resistance, so there's a little bit of slowdown when you put, let's say, your copper wire. You put a copper wire, you have a wire plugged into your battery, plugged into your light bulb. There's some energy along that wire that gets lost. Except in one case, and that is the case of what we call a superconductor. A superconductor is a material, there's very few of them, and they usually only operate at extremely, extremely low temperatures, and that provides absolutely no resistance. And so actually science is on the hunt right now or they've been on the hunt for quite a while actually, for the perfect superconductor, which would be a superconductor at room temperature. Right now, to make a material conduct things with absolutely no resistance, none, zero, zilch. So what you need to do to make these materials, we're gonna have an image of these materials, is that off the top of my head. What you need to do to make them superconducting is you need to take them and you need to cool them down. Now, different materials need to be cooled different amounts. Some materials need to be cooled down to nearly absolute zero, which we discussed in previous times. Some materials are just only negative 200. Only negative 150, whatever it is. And now, which is still extremely cold and extremely hard to get that. Although they spend absolutely no energy putting current through these materials, they start, let's say you have 5 volts, it goes through, it's still 5 volts, no resistance at all. However, there was a slight issue because to get that material to do that costs a lot of energy. So there's currently a hunt on right now for a superconducting material that works at room temperature. There's actually a fun story. There was this bunch of scientists, they were having a party, there was wine involved, and they said, hey, why don't we test the conductivity of different materials? And so they started testing, and this is what scientists do at a party apparently, and they noticed one of these materials that if they dipped it in wine first, it would conduct better. So go figure, there's a scientific discovery made that if you dip certain materials in wine, they superconduct at a lower temperature. So let's just put this right here. Superconduction means that it offers no resistance at all. A regular conductor, as we just talked about, offers very little resistance to, in our terms, for our purposes, the flow of electricity. And an insulator is the opposite of all those. It offers a lot of resistance, if not all resistance. So to illustrate how conduction works, and to therefore understand why certain materials work very quickly and certain materials are very slow at conducting things, or very resistant insulators, let's head over now to a stop motion video by Schiffman Studios. This is a circuit. This circuit is conducting electricity. But how does conductivity work? So let's take a closer look at the atoms that make up our wire. So this is a nucleus, and surrounding the nucleus, as we've previously discussed, are shells of electrons. So now here comes an electron from the buildup of electrons in the battery. That electron would like to force its way into this atom. When it forces its way into that atom, it replaces another electron. That electron goes to the next atom in line and does that same thing. And so on and so forth, until you get all the way to the positive terminal of the battery. All right, everyone, that is that. I hope everyone enjoyed that little video we just made there. So what this electron can do is it knocks off one of the electrons of the atom, which then knocks off the next one, and the next one, the next one, and so on. And that causes there to be a flow of electricity from one place to another. Right, as in the electrons that are, so don't think, if you were to go, if some of your grandchildren were to go and to invent a electron pencil, which basically means you can go and you can write on an electron. If you were to write, say, sign your name with your electron pencil on an electron inside the battery and then hook it up, you would not have that electron coming back to the positive side. What you would have is that electron knocks off the first one from the first atom in line, which then knocks from the next and the next and the next and the next, and they keep knocking each other until one of them goes, until all the way at the other side, one of those electrons gets knocked into the positive side of the battery. So it's not quite what you were imagining when we were showing you a river. It's not quite like a river. It's more actually, you're gonna probably learn about this, you may have already learned about this, I don't know, like a wave. If you have a wave in the ocean, the water isn't moving, it's just transferring force. So that's very similar to what's happening here. It's just transferring the force along. You can try this. You can test it at home. If you take a line of marbles and you take a marble and you hit one end of the line, the last one is going to fall off. Not that one. That one is going to stop moving. And it's going to transfer, the force is going to transfer along the line, and the last one is going to fall off the table. Now, if you don't have them continue, experiment. Take 2 pieces of paper or pieces of cardboard, make a little container, and have a line of marbles inside. Have one marble and hit the end. You'll notice that the last one is going to fall off. The rest of them are going to stay. One is going to fall off. And that is essentially what is happening with the electrons. One electron comes and knocks into the next one, which knocks into the next one, knocks into the next one, and so on. And so here's the thing though, why is it that certain materials can do that very easily? When we talk about superconductors, they can do that so easily that there's no resistance at all. We talk about regular conductors, there is very little resistance. This is very easy. It's not as easy as a superconductor, but it's still easy for them to trade off electrons, for that knocking to happen. Whereas insulators, it's nearly impossible. It nearly doesn't move at all. So what's the difference? What is the difference between them? So to illustrate the difference between them, we actually have to head over to YBH, because in YBH there's a very specific chart in the science lab that I need to show you. So let's head over there. We'll be right back. So over here we have the periodic table of elements. So now in one side you have hydrogen and lithium, beryllium, sodium, magnesium, all those things. You can check it up, and we're going to include a fuller, clearer version of what you're going to see here on your screen. But on this side, so you have those things, and then all the way over here, you have the silver, palladium, rhodium, gold, platinum, all these metals over here. And over here you have things like helium, neon, krypton. That's a real thing. It's not something that made up by Superman. Anyway, radon, xenon, all those things. So, you just heard a lot of funny words, and you've heard a lot of funny names for elements, and now let's talk about for a moment. Remember we talked about the shells of the atoms? That there's the atom, that there's the, we talked about that there's the nucleus in the middle, and then around the nucleus there's different shells of electrons. The nucleus is the protons and the neutrons, and then the electrons, we said there's 2, 8, 16, 32, etc. But I'm not sure if we mentioned then that if an atom has 8 electrons in its outer shell, it's good. It's happy, it does not need any more, it does not want any more, and it will not accept any more. The atoms that have a full set of 8 in their outer shell, now there could be more than 8 in the outer shell, but if they're up at least 8 in the outer shell, it's good, it's not taking any more. We call those the noble gases. They do not react with anything. They are inert. They are what we call inert, meaning they're non-reactive. So we have these gases, they're helium, neon, argon, krypton, xenon, radon. If you were to go to a party balloon and you're to open the helium and you're going to take a lighter and you put it next to it, you're going to probably burst the balloon, but the helium is not going to catch fire. Right? It does not react as nothing happens with helium. It cannot be affected by pretty much anything. It does not combine, does not mish, does not match, does not do anything. Right? Now, all the way on the other side, we have hydrogen. And hydrogen is the smallest atom, but it also it's one of the most common atoms. You'll find it everywhere you turn your sink, hydrogen is coming out, and oxygen bound together. See, hydrogen has only 1 electron, 1 proton, and 1 neutron. We discussed this. And what hydrogen does is it binds on to everything. The reason why it will bind to everything is because it's only 1 electron floating there. So it wants to find something, it wants to stick into something, right? Now, the way that this table is arranged is that the ones that have 1 in their outer ring are on this side. The ones that have 8 in their outer ring are on this side. And as you go this way, you start here as 1, now it goes into 2, 3, 4, 5, 6, 7, 8. Right, 7 is like this bit, and 8 is here. You guys can do the math if you want to as to what the rings will be. Hey everybody, I just realized as I was editing that I never actually explained why we care about the different shells of the atoms in terms of conducting electricity. So I'm going to do that right now. And when we talk about conducting electricity, we care, like we showed with the stop motion video with the guy with the hammer, that was actually made right over there. What that did is it took an electron from the outer shell and removed it and replaced it with another electron. And so now you can't do that if the shell is complete, because then it's like, nope, not new one, bye. We have enough electrons here, we're not taking any more. That's why I kept saying, no more, it's good. Well, we care about that it's good is because it therefore won't accept new electrons and won't release electrons from its outer shell. Now, if it's less than that, then it will. So anything less than a complete shell of 8 can accept other and can therefore conduct electricity. So now there may be other practical reasons why I can't conduct electricity, namely, gases are not particularly good at conducting electricity simply because they're gas. You wouldn't have pipes in your house made out of hydrogen simply because it would catch fire. There's a very low heat tolerance. Copper, on the other hand, has a very high heat tolerance within reason. It will eventually melt, but not immediately. And it, like most metals, are in the 2 to 4 range of how many electrons are in their outer layer. So there is some resistance. They have something of a shell, but they still have a weak enough outer shell of the atom, an outer shell of electrons, to remove an electron and to insert a new electron, and thereby making the flow of electricity. So that's what we keep talking about, reactive, how reactive it is, and we keep talking about if it's good, if it's finished. That's what all those terms mean. So let's get back to YBH, or for you, I'm going to finish editing, but you get the idea. But the point being is that the further you get here the less reactive they are. And the further you go this way, the more reactive they are. All right, everyone, we are back on my front stoop. And so I think we now understand how insulators work, how conductors work, how superconductors work. And so that is my time for today. I hope you all enjoyed the stop motion. If you did, just let me know. If the voiceover is a brand new microphone, so let me know if you can tell the difference. Either way, I hope you all have a wonderful, wonderful day. I hope you enjoy the sunshine. It's going to be for Thursday, so hopefully there's sunshine on Thursday, but if not, enjoy the sunshine when I'm filming. Anyway, have a wonderful day, and I will see you all tomorrow.